a few more examples of being able to use areas to be able to evaluate integrals, one of which is such that we have the graph and we have some areas that are bound by the function over some different endpoints. So we have this function, we have 4 different endpoints, A, B, C, and D. And we're just going to go ahead and use the graphs to be able, and the areas to evaluate the integrals. All right, so a really easy example, we have lower bound A, upper bound B of the function. So we're going from A to B. All right, and we can clearly see that that's 12. Okay, really nice and easy. We go from B to C. All right, now notice that the area is below the x-axis. So in this case, it would be -10. All right, so anytime you have an area that's below the axis, count that as a negative value for the integral. Even though there's no such thing as negative area, we just consider it as negative. And then if it's above the axis, count it as positive. From A to C, that means that we're just going to add the two areas together. All right, so really it goes back to that rule where you can partition and break up your integrals. So this is going to be from A to B of f of x dx plus integral from B to C of f of x dx, which is going to be 12 plus -10, otherwise known as 2. All right, so nice and easy for us there. Now finally, we have from B to D. All right, so that's going to span this length. And it's actually pretty easy. Once again, we're just going to figure out what BC is, figure out what CD is, and then we're just going to add those together. All right, so that's going to be equal to the integral from B to C of f of x dx, which we know to be -10, and then the integral from C to D of f of x dx, which we know to be 8, because that's what the area is right here in our picture. So we have -10 plus 8, otherwise known as -2. Okay, so those are pretty easy examples. If you're given the graph, just remember below the axis, and from there, just make sure that that it's in the specific order. Okay, so if it was from D to B, you'd have to use that negative rule. All right. Now, what if we wanted to take a Riemann sum and convert it into a definite integral? Okay, that's a pretty easy sort of operation as well. All we're going to do is every time we see a delta x sub I, we're just going to think of that as dx. This is going to be the integrand, in other words, the term that comprises the integral, and then the limits of integration are going to be the domain. All right, so in this case, we have the integral from 1 to 2. It's a pretty terrible integral sign. Let me try it again. Probably won't be any better. So we have integral from 1 to 2, a little bit better. And then the interior integrand is going to be your x cubed. Notice that I'm getting rid of the i's, plus x minus 1. And instead of delta x sub I, I'm going to call that dx. Okay, so really nice and easy for us to be able to convert a Riemann sum to a definite integral. All right, this x should be x sub I, so I'm going to squeeze that in here. All right, that's just a typo. And so our integral is going to be the integral from pi fourths to pi thirds. Those are our limits of integration. We have secant square of x plus x, and then instead of delta x sub I, that's going to be dx. And then finally, we have an absolute value of 2x minus 3. The bounds are from 0 to 4, so that's going to be the integral from 0 to 4, absolute 2x minus 3, and then we have a dx. Okay, so taking a Riemann sum, converting it into an integral, really easy. Okay, just chop off the i's, copy down everything that's after the summation sign, and instead of delta x sub I, that's going to be dx, and then the limits of integration are self-explanatory. All right, in the next video, we're going to take a look at being able to approximate the values of integrals using the left-hand rule and the right-hand rule.